Okay, for our final segment, I just want to take your knowledge of what we mean by electricity and what we mean by magnetism and kind of stretch it. Now, you notice that it says this is not going to be on the exam, so if you find this hard to understand, then don't worry about it, but I just find it kind of interesting. So imagine that you've got a wire and you're going to attach it to a capacitor. And then let's pretend that you've got positive charges that are going to be flowing in the wire. So that means that positive charges are going to appear on this plate, and then negative charges are going to appear on this plate. And then if you were to take a teeny tiny positive charge, you would find that it's going to be repelled by the positives and attracted to the negatives. And then what we end up drawing is the, which field? The electric field. And then another name for moving positive charges would be a current. So we would have a electrical current. Now normally I would just say it's the letter I, but there's a method to my madness here. So I'm going to put an E to stand for electrical. So this would be an electrical current made by electrical charges. But do you remember what pushes electrical charges? It was going to be the electric field. So an electric field is what's causing the electrical charges to make an electrical current. And then you can also have an electrical field inside the capacitor. And again, it's being made by electrical charges. So I wonder if there isn't something similar that we could do that would illustrate magnetism. And it turns out that we can. Now, a normal bar magnet is going to have a north pole and it's going to have a south pole. So what do you think would happen if we took a bar magnet and you break it in half? What do you get? Well, you get two new magnets. So if I take this one and then I break it in half, all that I'm going to end up with is another north pole, south pole, north pole, and then south pole. So it's impossible to isolate a north pole, but that doesn't stop scientists. So people like Einstein could think out of the box. So imagine that you could have an isolated north pole. What would that look like? So instead of having a current that is composed of positive charges, what would happen if you had a current that was composed of north poles? Now it can't really happen, but let's just say for the sake of argument that it does. So we're going to have a current made of north poles, so we're going to say I, but instead of E, it would be M. So this would be a magnetic current made of north poles that are moving through the wire. So just like over here, you would have north poles would begin to appear on this side of the plate, and then by conservation of magnetism, for every north pole you have, you'd have to have a south pole that would go with it. Okay, and then do you remember that you could take a teeny tiny north pole and place it in there? It would be repelled by these north poles and it would be attracted to these south poles over here. So this time we would get a field inside the capacitor, but this time it would not be an electric field, it would be a magnetic field. And so the first statement there says that magnetic charge makes the magnetic field. So the movement of magnetic charge, north poles, makes a magnetic current, and then also these north and south magnetic poles makes the magnetic field in there. But since you cannot separate a north and south pole, we just figured out here, there is no net magnetic charge and therefore no magnetic field. So you can't really make this, because for every north pole that would be traveling in the wire, there'd be a south pole to go with it, and so they would cancel, so there'd be no magnetic current. And similarly, in here, there would be no net magnetism. Okay, let's go on to the second one there. Moving electrical charge makes a electrical current. So that's this one here. So magnetic charge, or magnetic current, would have to be made by a magnetic field. So a magnetic field would make a magnetic current, and then you would have this magnetism in between the poles. So the second statement is that moving magnetic charge makes a magnetic current, but since there's no net magnetic poles, then again the current is going to be zero. So you have just as many south poles traveling in this wire as you would north poles, so again they cancel. So again, there is no such thing as a magnetic current. You have electrical currents, but not magnetic currents. And then the third statement says electrical currents and changing electrical fields make magnetism. So that currents make magnetism, and also changing electric fields make magnetism. So what would be the analogous thing when it comes to magnetism? So magnetic currents and changing magnetism makes the electric field. But there's no such thing as a magnetic current, so that one doesn't work. But what about the changing magnetic field makes the electric field? Yeah, that one is true. So that's this one over here. A changing magnetic field makes the electric field. So I don't know if you found that interesting or not, but I did. And that's all that's important, is what I think, right? Okay, good. So let's take one more break, and then finally, when we come back, we will take a quiz over what we have learned today. Okay?